Alright, this video is going to be on continuity of functions. So when you talked about continuity earlier on in math, you probably talked about it as a curve where if you followed it with your pencil, you wouldn't have to pick up your pencil to follow the curve. So that's kind of like the informal definition of continuity. Now that we're in calculus, we're going to look at the formal definition of continuity. So the definition is a function is continuous at a point A if the limit as x approaches A of the function is the same as where you evaluate the function for A. So there are three things that we will check. The first thing that we will check is we want to make sure that the function is defined at A. So f of A is defined. It means you can plug that number in for x and get a y value. The second thing we want to check is that the limit as x approaches A of that function exists. That limit exists. And what it means when a limit exists is that the left-hand limit and the right-hand limit agree with each other. So for a function to be continuous, then at that point there needs to be a limit. At that point you should be able to plug in that x value and have the function be defined. And last, you should be able to say that as x approaches A of the function, the limit is the y value that you get when you actually plug in A. Alright, so if we think about this in terms of pictures, because these really do make a lot of sense, you just have to think about it. So if we're looking at this in terms of pictures, it says that f of A is defined. So if we were to look at this curve, and your x and your y-axis can really be anywhere, it doesn't matter. Let me make it straight though. So if this is your curve, what it's saying is that if we choose a point A that's on the curve, A is defined. That means I can plug that number in for x and I can actually get an answer. The limit exists here, so this is not a case where you have like the two values portion where you've got like something like that. It's not this case. An asymptote can't be there because the limit would not exist there, and then you'd have like something like this. So that can't be possible. A limit has to exist. And the limit has to be whatever the y-coordinate is at the hole. So it can't, or at that point. You can't have something like a hole and say, okay, well, we've defined the point right here, and there's a limit that exists right here, and here's the limit right here. The limit has to be exactly that point. So it's saying it can't be a hole, can't be a vertical asymptote, can't be some sort of jump like this. It has to be just a continuous graph. You can follow along with your finger without picking your finger up. So these are the three ways that we'll test it. Alright, so anything else, anything that makes a graph not continuous, we would call it a discontinuity. And so here we're going to look at the types of discontinuity that we have. So the first type of discontinuity that we would have is a removable discontinuity. And a removable discontinuity says that it is possible to remove the discontinuity by redefining f at just that single point. So basically they're talking about a hole. And they're saying that a hole is a removable discontinuity because let's say I have an equation that gives me a graph like this where there's a hole. Well, I could turn that equation, I could write a piecewise function instead and keep this as one part of the piecewise function and then have the second piece of the piecewise function go in and fill in that hole. And then that would force that to be continuous. So that is one type of discontinuity. So the reason behind this discontinuity, we might say, is that f of a at this point is probably undefined. That's what happens at a hole. Okay, another type of discontinuity is a jump discontinuity. And a jump discontinuity is where the function jumps from one value to the other. And that's what I mentioned above where you have something like this. So this value, we would say, that's a jump right there. You're going to see this in piecewise functions. You might see it in functions that involve absolute value as well. And the problem with this is that you have that jump there, and so if we go back to those three definitions, the issue here is that your left-hand limit and your right-hand limit would not agree with each other, and so the limit would not actually exist for that function. So I would say with this one, the problem with the jump right there is that the limit as x goes to a of f of x does not exist, and it doesn't exist because there's two values there. All right, and then the last one is infinite. An infinite discontinuity is where the function goes to positive or negative infinity. So on this one, this would be like if you have like a vertical asymptote and the function would not have a limit there because limits at vertical asymptotes do not exist. So we would say in this case, you're not going to be able to find, well, this kind of works with all three of them. This, you would be undefined. The function would most likely be undefined at that point unless it was a piecewise and they put a point there. You would also say the limit does not exist at that point. The left-hand and the right-hand limits don't agree. And then you could also say that when, for the third option, that when you plug in that value, that's not what the limit does equal. So this one kind of violates all of them. All right. So also in your notes for continuity, a function is continuous on an interval if it is continuous at every number on that interval. So what that means is if you say a graph is continuous from negative infinity to positive infinity, there better not be a hole anywhere on that graph. If there is maybe a hole at like negative 500, then you could say that the graph is continuous between negative 500 and positive infinity and just not include that part where it's discontinuous. But you have to make sure that if you say a graph is continuous on an interval, that it really is continuous at every single point between those numbers. There's a few functions that are continuous everywhere that their domain is defined. So functions that are continuous everywhere on their domain are polynomial functions, rational functions. And rational is kind of a weird one because that's where all the vertical asymptotes and holes and all of the funky stuff comes from, is from having factors that don't cancel out in the denominator. And that's where your vertical asymptotes come from, or factors that do cancel out, and that's where your holes come from. And the reason we can say that rational functions are continuous everywhere on their domain is that those values, those vertical asymptotes, those holes, those values are excluded from the domain already. And so that means whatever's left over is continuous. So a polynomial function, rational function, root function, so square root, cube root, etc., and then the trig functions. So if you have found the domain of these functions, then you already know where these functions are continuous. So oftentimes you'll notice that the domain of something and where it's continuous are very closely related. Piecewise functions would be the huge exception to this rule. When you have a piecewise function, you can't necessarily find the domain and say that the domain is automatically where the graph is continuous. You have to do a little bit more practicing with the numbers and seeing what thing works and what thing doesn't work, and that sort of thing. It's not as cut and dry. So we're going to do a few examples utilizing these ideas, because this is, at this point, I haven't taught you a skill. We've just been talking about definitions and how things work. So for example, with this, we're going to be looking at functions, and we're going to ask where the function is discontinuous. And we're going to ask why it's discontinuous and what type of discontinuity it has. So for our first example, we're going to look at the function, the rational function, f of x equals x squared minus x minus 2 divided by x minus 2. And when I look at this, I can see that this function is discontinuous at 2. I can't plug 2 in. So I'm going to say that we are discontinuous at x equals 2. And the reason that we're discontinuous at x equals 2 is because f of 2 is undefined. If we think about those three things that we use to prove that, that functions are continuous, one of them was that you have to be defined at that point, and here you're not. You're undefined at that point. All right. The type of discontinuity we have, this sort of discontinuity, it could be a vertical asymptote, or it could also be a hole. So we have to kind of factor this to figure out which one we're talking about. So this would be x minus 2 and x plus 1 when I factor it. And so that means that that discontinuity is a hole. And so the type of discontinuity is removable. That's a hole, so it's a removable discontinuity. All right, for this one, we're going to take a very similar function. We're going to start off with this one. We're going to make it a piecewise function, saying that most of the piecewise function is defined here, and that's only if x does not equal 2. And then it's going to equal 1 if x does equal 2. Now for this one, again, I'm going to say that the discontinuity here is at x equals 2, but it's for a different reason this time. So this time you can see that x is defined at 2, but we can't plug 2 in right here. So that means that we are defining it somewhere else. We're using the 1 right there. And if we think about plugging 2 in, like where the hole would have been, the hole actually would have been at the point 2 for x, and the y value there would have been 3. So that would have been the hole, that would have been plugging the hole. If they'd put a 3 here, then we could have said, yeah, this graph is actually continuous. So now we're defined at 2, but the y coordinate is in a different spot than we would have expected it to be, and that's the problem here. The problem here is that the limit as x approaches 2 of f of x does not equal what we would get if we plug 2 into the function. So the limit as x approaches 2 of this part right here would have been 3. But what we actually get when we plug in 2 is a 1. So that's the problem with this one. That means that this type of discontinuity right here is also removable because we're still talking about that same hole. So the type is removable. All right, for this one, we're going to say f of x is another piecewise function So here at this one, I can see that something interesting is kind of happening where x equals 1, but the discontinuity actually happens at x equals 0, because that would make the denominator equal 0 in that fraction. So the discontinuity happens at x equals 0. The reason why is that the function, when I define it, when I plug in 0, I find that it's undefined. And if I consider what this is here, whenever we see the denominator equaling 0, that usually means there's a vertical asymptote or a hole. And in this case, we don't have a factor on the top and the bottom that cancel, and so that means we have a vertical asymptote happening here. So since we have a vertical asymptote, I would say that this is an infinite discontinuity. Infinite discontinuity. Okay. For another type of example, we want to look at on what intervals certain functions are continuous. So the first one we're going to look at is a polynomial function. We're going to say f of x is x to the 100 minus 2x to the 37th power plus 75. And the point of this one is your calculator can't handle that. Those exponents are way too large. So you have to think about what you know about polynomial functions, and what we know is that they are continuous on their entire domain. And the domain of a polynomial function is always from negative infinity to positive infinity. So we're going to say that this function is continuous from negative infinity to positive infinity. And I don't have to do a lot of math to know that, just because I already knew that polynomial functions were continuous. Next, we'll go ahead and look at a rational function. So we're going to look at x squared plus 2x plus 17 over x squared minus 1. And if you look at this function, you can see that the top is not factorable. There's nothing that multiplies to 17 and adds to 2. So that means for us, we know there's no holes. There can't be a hole in this graph. So I'm just going to factor the bottom to see what my vertical asymptotes would be. And so once I can see that, I know that I have vertical asymptotes at -1 and +1. And so that means when I write the domain for this function, I want to include those numbers. And since this is a rational function, I know that this graph is continuous on its domain. So once I write the domain down, that means that I have found the continuous interval. So this is going to be all x values with the exception of -1 and +1. So I'm going to say negative infinity to -1, -1 to +1, and +1 to infinity. This one's going to be a little bit more difficult because we're going to look at a piecewise function, and those are a little bit less straightforward, since these were not ones where we could say, oh, find the domain, and then you actually know what the continuity is. So for this one, you can see over here, based on the drawing, that this is definitely undefined at 0. So we're not going to include that as part of where it's continuous, because it's not defined, so automatically it can't be continuous there. And that kind of works because right here we would expect to see some sort of asymptote or something. But we also have to consider what's happening here. If you were to plug in a 1, that would not be within your domain. You can't plug in 1 there, because that says the x is greater than 0 for this function. So we do have something happening there. It looks like it's probably a vertical asymptote. It's definitely a vertical asymptote. So when I want to write where this is continuous, I'm going to go ahead and make sure that I exclude the 1 here, and I need to exclude the 0 here, because neither one of those would work. So this is going to be continuous from negative infinity to 0, and then 0 to 1, and then 1 to infinity. And there was no... These are actually numbers that are excluded from the domain. So in this case, we happen to say that the domain is also the interval where this function is continuous, but it is possible for that to not be the case. They could have added something in here and told us that the function was defined at 0, and then we would have had to check it to see if it really made sense for the problem to include 0. So All right, and then we'll look at one more, and this one's just going to be like a weird combination of a bunch of different things. So we're going to say square root of x plus x plus 1 over x minus 1 minus x plus 1 over x squared plus 1. So this is a combination. This is a function that's a combination of functions. We've got two rational functions that are continuous on their domain. And we have a root, which is also continuous on its domain. So if we can find the domain of all these different pieces, then we will know ultimately where this one is continuous. So the domain for this piece right here, we know that we can't plug a negative underneath the square root, and so we're going to say that just for this piece right here, that the domain is that x has to be greater than or equal to 0. For the domain of this piece, I know that I can't use positive 1. And then over here, I don't have anything excluded because that's x squared plus 1. That's not factorable. It doesn't matter what you plug in for x. It's always going to be a positive number plus a 1. So that denominator can never equal 0 anyway. So when we describe where this function is continuous, we just have to take what is the most limited between these two things. So I'm saying all the numbers that are greater than or equal to 0 except for 1. So my interval where this function is continuous would be 0 to 1. We're including 0, and then 1 to infinity. Okay, and I know the video is getting really long, but we do have one more type of problem we want to look at. So here, we are going to find A and B to make f of x continuous. And f of x is actually a piecewise function. So it's 2 if x is less than or equal to negative 1. It's going to be ax plus b if the x is between negative 1 and 3. And it's going to be negative 2 if x is greater than or equal to 3. So here we need to remember what makes a function continuous, and that is that the function is defined at x. So we got to make sure that that happens. And we have to say that the left-hand limit and the right-hand limit agree with each other so that the limit exists. And the limit has to be whatever it would be if you evaluate it right there. So those are the three things we need to look for. So that means the places where we are concerned about this function is we're concerned what's happening at negative 1, and we're concerned what's happening at 3. Those are the two things that are going to help us figure out this problem. So I know that I want these two things to match up on the graph. I don't want to have a jump there. I want those to equal each other at that x value of negative 1. So what I'm going to do is I'm going to set them equal to each other. 2 equals ax plus b, and I'm going to plug in the negative 1 there. So 2 equals a times negative 1 is negative a plus b. That is one thing that I want to be true. The other thing that I want to be true is at 3, I want these two things to equal each other. So here I'm going to go ahead and say that ax plus b is going to equal negative 2, and I want that specifically to be the case when the x value is 3. So that means that we could plug 3 into the equation, we could plug negative 1 into the equation, and you would be able to evaluate them. Here, by setting them equal, we're forcing the left-hand limit and the right-hand limit to agree. And we're saying that when the left-hand limit and the right-hand limit do agree, it's agreeing at that y value that you would get if you plugged that x value in specifically. So now, this is kind of going back to early on, our Math 1 days, where we have a system of equations, and I'm going to go ahead and solve this using elimination. And so I'm going to take this top line right here, I'm going to multiply it by 3, because I can see that the a's would cancel out if I do that. And you can multiply it differently, that's just the first way that I saw. You actually could have gotten rid of the b's pretty easily. So when I add those together, I get 4 equals 4b. And so that tells me that b equals 1. So I just solved for b. And now I can go up and plug b into one of the two equations. It does not matter which one. So I'll go ahead and say 3a plus 1 equals negative 2. And I can subtract that 1 over, and I get 3a equals negative 3. And so the a value there is negative 1.